So now that we've explored the Gauss-Jordan elimination method, let's put it to use. Here's a linear system. We've got 4 equations and 6 variables. So that's quite a bit more complex than the type that you might try to use the substitution method for example. So it's cases like this where this algorithm really shines. So what are we going to do first? We're going to write down the augmented matrix, right? And then once we write down the augmented matrix, we're going to apply row operations, which are dictated by the Gauss-Jordan elimination method. And what that's going to accomplish is it's going to turn our augmented matrix into reduced or echelon form. And once we get to that point, we'll be in a position where we can write down what's called the general solution. Because what we're going to see is this is an example of a linear system with infinitely many solutions. So this example is also going to serve as an illustration of how to handle that situation and how to actually express that infinite solution set in an organized fashion that's useful. So here's the augmented matrix. And the first thing we're going to do, what I won't do is I won't go keep flipping back to the precise statement of the algorithm. We're just going to apply it right now. So I encourage you, though, at any point, if you are a little bit confused on which step we're on, to pause the video frequently and flip back to the actual statement of the Gauss-Jordan elimination method, and you can follow along in precisely with the steps. But for now, I'm just going to go through it in a rough manner. So the first thing we need to do is we need to find our first pivot column. So remember what to do. That's what you want to do is you just go through each of the columns, starting at the leftmost one, and you stop as soon as you get to a column that doesn't consist entirely of zeros. And quite often that's going to be the first column, right? So our first column has no zero, or pardon me, has a non-zero entry. In fact, it has 3 non-zero entries, and that's good enough. So we'll stop and let our first column be the pivot column, the first pivot column. And if you remember what the rest of step 1 says, once you identify the pivot column, the top entry of that pivot column, that's going to be our first pivot position. Okay, now the next thing we need to do is we need to make sure that that pivot position is occupied by a non-zero entry. So if there had been a 0 in this position, then we would need to swap rows as necessary to make sure that there's not a 0 there. But since there's already a non-zero entry there, we're good to proceed to step 3, which at that point, step 3 is saying, okay, now make sure there are no non-zero entries below that pivot position. So the way we're going to deal with that is we're going to turn both of these twos into zeros. And the way we're going to do that is we're going to subtract the first row an appropriate number of times. So we'll take row 2. Here's what I mean. Take row 2 and replace it with row 2 minus 2 row 1. And then if we subtract row 1 from row 2 twice, that's going to have the effect of turning this 2 into a 0. And then if we do the same thing for row 4, so I'll take row 4 and replace it with row 4 minus 2 row 1, that's going to have the effect of turning this 2 into a 0. So let's go ahead and work that out. So I'm going to copy and paste this matrix here. And then what I'm going to do is I'm just going to erase the third row and the fourth row, because the other rows are staying the same. Okay, so our second row, let's just subtract the first row twice. So we're going to have 0 and then 0 again. And then here we got negative 5 minus negative 2 twice. So that's like adding positive 4. So we're going to have a negative 1 here. The negative 2 won't change. 4 minus 2 times 2 is going to be 4 minus 4. Then we've got negative 3 minus 2 times 0, which is just negative 3. And then similarly, the last entry is just going to be a negative 1 still. Okay, so the fourth row, we're going to subtract row 1 twice. So we're going to have 2 minus 2, 6 minus 6, 0 minus negative 4. So that's actually going to be 0 plus 4. Then we'll have 8 minus 0, 4 minus 4, 18 minus 0, and then 6 minus 0. So that's what happens when we perform those 2 row operations. And you can see they were successful. We successfully turned these 3 entries into zeros. Okay, so now we're at the point now where we're going to loop back but restrict our focus to a submatrix. So I'm going to draw just a line here. This is not a real line. Remember, it's just an imaginary line to help us keep things organized. And all this is for is just to help us keep track of the submatrix that we're reducing our focus on when we now go back and do the next iteration of the first half of the Gauss-Jordan elimination method. So we're going to find the first non-zero column. So that column consists entirely of zeros. That column consists entirely of zeros, so keep going. This column does not consist entirely of zeros. In fact, it entirely consists of non-zeros. So the next thing is to say, okay, this is now going to be our next pivot column. The top entry in that column is going to be the pivot position. So this -1, that's going to be our next pivot position. And once we've selected that pivot position, what do we want to do? We need to make sure it is occupied by a non-zero entry. And again, it is. So we don't need to swap any rows around. It's already occupied by a non-zero entry. But the next step of the algorithm says, well, make sure there's no non-zero entries below that pivot position. So our attention now is focused on the 5 and the 4. Those are our next challenge. We need to make those into zeros. So what you always want to do is you always want to add or subtract an appropriate multiple of your pivot row. To use that pivot whatever entries in that pivot position, that's the entry you're focused on. That's what's going to determine what multiple you add. So in this case, we're adding a multiple of row 2 to row 3, and we're going to add a multiple of row 2 to row 4, and the multiples are going to be determined by whatever is necessary to turn that 5 and the 4 into 0. So in this case, since our pivot position contains a -1, we're going to want to add row 2 to row 5, to add row 2 to row 3, but we'll do it 5 times. And that's going to have the effect of turning that 5 into a 0. And then we can add row 2 to row 4 times, and that's going to have the effect of turning that 4 into a 0. So let's go ahead and write those row operations down. So take row 3 and replace it with row 3 plus 5, row 2. Then we're going to take row 4 and replace it with row 4 plus 4, row 2. And that is going to accomplish what we want. So let's go ahead and perform those operations. So I'll go ahead and just erase the rows that are going to change. And what are we going to have? So the third row is going to become 0, 0, 0, well, 0. You can check that this is the case. Pause it if you want and check that my arithmetic's correct. But actually, the third row is going to turn into an entire row of zeros. And the fourth row, well, we're going to have 0, 0, 0, 0 again, 0. And then this one will be 18 plus 4 times -3. So that's going to be 18 plus -12, which is +6. And then for the last entry, we'll have 6 plus 4 times -1. That's going to be 6 minus 4, which ends up being 2. Okay, so that brings us now to the stage where we have finished our second iteration, and now we're going to go back to the beginning of the algorithm, but we're going to reduce our focus to an even smaller submatrix. Now we're going to look at only the bottom 2 rows, and we are going to find our next pivot column. So remember what to do. We start with the first column, just keep working your way to the right until you find a column that has at least one non-zero entry. And here you go. This one has a non-zero entry, right? It's got a 6 involved. So that is going to be our next pivot row, our next pivot column. And the top entry of that row is going to be our next pivot position. And once we select our pivot position, we need to make sure that that position contains an entry that's non-zero. But right now it does contain a 0, so we need to do a swap. And the only rows that are remaining to swap, because you have to work, when you swap a row, when you swap rows here to turn that pivot position into a non-zero entry, you can only swap it with rows below. You wouldn't want to say swap it rows 2 and 3. If I were to swap rows 2 and 3, then that would have the effect of moving this -3 here, and it would certainly get us a non-zero entry in that pivot position. But then it wouldn't be a pivot position anymore, because we would introduce non-zero entries in these elements, and then this would not be a leading entry, so it can't be a pivot position. So when you're swapping rows to get rid of a non-zero pivot entry, you only can swap with rows that are below that pivot position. So that's a bit of a digression, but that's important to say. So we only have one option. There's no mystery. We have to swap row 3 with row 4. Okay, so that'll be a quick operation. Make a quick copy of this again. And I'm going to actually just erase that pivot. So I'm just going to be creative here in how I move these entries around. So that's rows 3 and 4. This is row 4. It's going to become the new row 3. And then the old row 3 is going to become the new row 4. And then I'll put the pivot position back. Okay, so that is the end of step 2. And then now we want to make sure that all the entries that are below that pivot position are equal to 0. But the one I just circled is the only entry that's below that pivot position, and it's already 0. So fantastic. That means we don't have to worry about that. And now we would, like if you're going through the algorithm carefully, you're going to move your focus down to this smaller part of the matrix, and you're going to say, okay, now start the algorithm over again, but look at this row. But you're going to find, when you go to find a pivot column, there are no pivot columns because none of those columns have a non-zero entry. And so you're going to end up finding that you can't find a pivot column. But if that ever happens, basically what happens is once you get down to the rows of zeros, you stop. You stop the first half and you're done turning your matrix into a row echelon form matrix. Why don't I just erase this line here? Let's take a look. We have a row echelon form matrix, right? All the rows of zeros are at the bottom. There's only one, and it's down at the bottom. Check the form of the leading ones, or leading entries, sorry. We've got ourselves a downward facing staircase to the right. And all the entries below the leading entries, all the entries below the leading entries are all equal to 0. So this is in row echelon form. So this concludes the portion of the Gauss-Jordan elimination method that is called the forward phase, the part where you get your matrix into row echelon form. I actually skipped over that part. I meant to comment on it, but I actually missed this line in the last page. So let's go back and do that now. Steps 1 to 4, that's the part we just did. We've completed step 4. So we've finished the forward phase. That's the part of the Gauss-Jordan elimination that turns your matrix into row echelon form. And then if you want to get into reduced row echelon form, then you continue on and complete steps 5, 6, and 7. And that technically this should include 5. So let's, here I can cheat here. You could make a modification. This should say 5. Steps 5 to 7 are referred to as the backward phase. That's the part where you take your row echelon form matrix and you turn it into reduced row echelon form. So yeah, make that little change here. I mean, it's not a big deal. This is not something I'm ever going to be picky about, but just so you're aware, the part where you start the second half of the algorithm, that's called the backward phase, where you turn your row echelon form matrix into a reduced row echelon form. So you do that if you want to go further. And in this case, we do. We want to get it into reduced row echelon form. So now we're going to start that phase. And what you do is you just you apply a couple of steps to each of your pivot rows. In particular, you start with looking at the entry that's in the pivot position. So here we're going to look at the 6, and the first step is we need to, and just to emphasize too, you're going to do something to each of the pivot rows, but you're going to start at the bottom. So we're going to start with this one, then we're going to go up to this one, and then we're going to go up to this one, and then we'll be done. So for the 6, our first focus is, well, it's got to be a 1, because all the leading entries in a reduced row echelon form matrix have to be equal to 1. So let's start by scaling that row. So we'll take row 3, and how do you make a 6 into a 1? By multiplying it by something. Multiply it by 1 over 6. And that'll turn that entry into a 1. So let's go ahead and duplicate this. So now I'm going to erase the row that's going to change, and then but I am going to put that pivot position back in. It helps to keep track of where your pivots are. It helps remind you what to do next. So okay, what's going to happen if we multiply each of those entries by 1/3? Well, unfortunately, we're going to have a fraction involved, and sometimes it's unavoidable. Sometimes you're going to have fractions in this, and it slows things down, because fraction arithmetic, when you're doing this many calculations, fraction arithmetic is definitely, it can be an irritation or annoyance, but the best thing to do is just be careful, go slow, and just, you know how to deal with fractions. You just have to follow the rules carefully, but it's not the time to rush, because that'll just lead to frustration. Okay, so we've turned that leading entry into a positive 1. Next, we need to look at the leading entries that are above, pardon me, we need to look at the entries that are above that leading 1, and we need to make sure they're all equal to 0. And what we're going to do is we're going to use that leading 1 to make them 0. So the -3 is the only problem, right? It's the -3 that we need to deal with. So how can we turn that into a 0 using our leading 1 down below? Just add it 3 times, right? And that'll accomplish it. So we're going to take row 3, pardon me, we're going to take, well, I should say it this way, we're going to take row 2 and replace it with row 2 plus 3, row 3. Okay, so now what'll that do? Let's make a copy of this matrix. And this, well, actually, how much do I need to really erase here? We're adding row 3 to row 2 3 times. Are these zeros gonna change anything? The answer is no. If we add these 5 zeros to these 5 entries, because that's going to happen 3 times, we're going to add them all those zeros, it's going to do absolutely nothing. If you add 0 to something 3 times, it doesn't change a thing. The only entries that are going to change are these two. So I'll erase the -3 and the -1. Those are the only things that are going to change. And so what's going to happen, if we add the 1 to the -3 3 times, we're going to get -3 plus 3, which is 0. And if we add 1/3 to -1 3 times, this is going to be -1 plus 1. So that's going to be a 0 as well. So now our last column is perfect. We've got a 1 as our leading entry, and all the entries above it are 0. So now we're done with that pivot entry. Now we can go to this pivot. So that needs to be turned into 1, first of all, and then all the non-zero entries above it must be cleared out and turned into 0. So let's start by turning that -1 into a positive 1. So we'll take row 2, just flip the sign of every entry in that row. Multiply the whole row by -1, and that will do it. So take row 2 and multiply it by -1, row 2. That's an easy change. So I can again just kind of cheat here and just erase the numbers that are non-zero, because those are the only ones that are going to change, right? You multiply all the zeros by -1, you're going to change absolutely nothing. I'm just going to put the pivot position back in. So what's going to happen? The -1 is going to become a positive 1, and the -2 is going to become a positive 2. So great, we've got that sorted out. And then lastly, or not lastly, we still need to turn that into a 0. Right, that the 1 in this pivot position has to be the only non-zero entry in that column. The entries above it have to be turned into zeros. So we can get rid of this -2. How do we get rid of the -2? Using that pivot entry of positive 1, just add the 1 twice. So but we have to add the whole row, of course, right? So we're going to take row 1 and replace it with row 1 plus 2, row 2. Okay, so that's how we can get rid of that -2. So what's going to happen? And I can just get away with only erasing those 2 entries. Why? Because these are the only 2 non-zero entries in that row. So when you add all these zeros to the entries above it twice, it's not going to make any change. And if you add these zeros to the entries above those 2, if you add those 2 zeros to the entries above, they're not going to make any changes either. It's just when you add these 2 entries to these 2 entries, that's the only place you're going to make a change. Okay, so what's going to happen? Well, when we add 1 to -2 twice, we're going to introduce a 0, because it's just -2 plus 2. And then for this entry here, we're going to have 0 plus 2 times 2, which is just 0 plus 4. So we'll have ourselves a 4 there. Okay, so that concludes the cleanup, let's say, for lack of a better phrase, the cleanup of this pivot entry. And then lastly, we look at our top pivot entry. But the only thing that would possibly be a concern is that it might not be equal to 1. You don't have to worry about any entries above it because it's the top row. So great. We've got, it's already equal to 1, and it's in the top row, so there's no entries above it. So we can just check that one off our list. We're done with that pivot entry as well. This is in reduced echelon form, right? You could start. Here's an exercise for you. Pause the video, look back at the conditions for a reduced echelon form matrix, and verify that they're all satisfied one at a time. and then you can resume this video and I'll show you how to write down the general solution. Okay, so uh, let me pause here and introduce some terminology. Okay, so remember there was 6 variables in this linear system. That's where this came from. There was 6 variables. So each of these columns corresponds to a variable. So let me just write a reminder. I'll do it up here because then it won't be in the way. So this is x1. This is x2, x3, x4, x5, and x6, just as a reminder, so we have it on the screen. These variables, or these columns all correspond, that was bugging me, I'm just going to fix it. These columns all correspond to variables. Take a look at which of those variables correspond to pivot columns. In other words, correspond to columns that actually have pivot positions in them. So x1 corresponds to a pivot column, x3 corresponds to a pivot column, and x6 corresponds to a pivot column. So because those variables correspond to pivot columns, we call them basic variables. So I'm just going to add that as a comment. x1, x3, and x5 are basic variables. Okay, so that's an important term. And the other variables, the ones that don't correspond to pivot columns, so x2, x4, and x5, those are called free variables because they correspond to columns which are not pivot columns. They don't have leading entries or leading ones in them. So let's finish that out. So x2, x4. I made a mistake here. This should have been an x6. Pardon me. In case that threw anyone off, because x1 and x3 and x6, it's x6 that it corresponds to a pivot row, pardon me, pivot column, not x5. So x2, x4, and x5 are not basic variables because they correspond to columns which are not pivot columns. So therefore, they're called free variables. So let's finish that off. So they are free variables. Okay, so what do you do with these variables? What's the difference? Well, there's lots of different ways to approach this. Here's what I like to do. I like to start at, I'm going to draw a little arrow here. Don't bother copying this down because I'm going to move it. I'm just going to take advantage of the fact that I'm working on a tablet here so I can move that arrow as I go. So, but you may not want to actually write it down because especially if you're working on actual paper. So that's the column that we're looking at right now. And you're just going to simply ask yourself a question. You're going to say, is that a pivot column? Does that, or equivalently, is the variable that this column corresponds to, is it a basic variable or is it a free variable? And if it's a basic variable, write out the equation that corresponds to the pivot row, right? This is the pivot row corresponding to that column. So write out the equation. And what is that equation? It's going to be x6 is equal to 1/3, which is awesome. That's nice and simple. It just tells us exactly what x6 has to be. Okay. Now you're going to move one column to the left. And you're going to ask yourself the same question. Is this a pivot column or not? So, or in other words, what you really are after is x5, is it a basic variable or a free variable? In this case, it's a free variable. So what we're going to do is we're going to assign it what's called a parameter. So what we're going to do is just introduce another symbol. Be careful. Don't use a symbol that you've already used in the problem. Make sure it's a new symbol. You can use whatever symbol you like, whatever letter you like. Just make sure it's not something that's already been used. But I would encourage you to follow the convention that is standard. And in this case, what I like to do is I like to use the letters S, T, and U. Or sometimes you'll use R. You'll usually use letters that are later down in the alphabet. But maybe not X and Y and Z or W. Because those are often reserved for other things. Although you do have flexibility. But the only thing that's a hard rule is that you can't use something that's already been used in the problem, because then that would cause ambiguity, and you'd start to run into confusion. So okay, x5 is a free variable, so we're going to assign it a parameter. I'm going to use the letter S. That's always the variable I use for the first parameter. And then, okay, so that takes care of that column. We're going to move one column to the left again. And again, that's another free variable. X4 is corresponding to a column that does not contain a pivot position and is not a pivot column. So x4 is a free variable. It's also going to get a parameter. So x4 is going to be given, I'm going to use the next letter in the alphabet, T. Okay, so that one is taken care of. Now we're going to move towards the third column, and that's a pivot column. So we're not going to assign a parameter to x3. We're going to write out the equation that corresponds to the pivot row. Okay, so what I mean is the pivot row that contains this pivot position. So we're going to write out the equation that corresponds to row 2. And that equation is x3 plus 2x4 is equal to 0. And then just isolate the variable that corresponds to this column. Isolate the basic variable that you're dealing with, right? x3 is a basic variable because it corresponds to a pivot column. So we're going to solve for x3. So we're going to get x3 is equal to negative 2x4. And okay, but we're not going to stop here. We're going to go one step further because x4, we've assigned a parameter to it. So actually, let's reuse that parameter here and actually substitute the t in for x4. So we get x3 is equal to not negative 2x4, but it is still equal to negative 2x4. But we're going to do better. We're going to write it as negative 2t instead. Okay, that takes care of that. We've solved for it. So now we're going to move over one more, and we got x2. x2 is another variable that corresponds to a non-pivot column. So it's a free variable. It's going to be assigned a parameter. So x2 is going to be the letter U. You get the next letter that comes after T, right? So these were my parameters that I chose. Okay, now we'll move one column over to get to x1. That's another pivot column. So we're not going to assign it a parameter. We're going to write out the equation that corresponds to the pivot row. So that's going to, which is going to be x1 plus 3x2 plus 4x4 plus 2x5 is equal to 0. And then solve for x1. Solve for the variable that corresponds to the column you're working on. And we're going to get x1 is negative 3x2 minus 4x4 minus 2x5. And then each of those variables are free variables. They've been assigned parameters. So plug those parameters in. So x2 was actually u, x4 was t, and then x5 was s. So we got minus 2s. So that completes our isolation of x1. So now that we've run through all the columns, now we're just going to do what we usually do. I'm going to delete this arrow because we're done with it. And we're going to just summarize everything in column form. So we got x1, x2, x3, x4, x5, and x6. And then put everything in. So x1, that was negative 3u minus 4t minus 2s. x2 was u. x3, and then you're just going to go back and look through this work and put everything together, right? So x3 was negative 2t. x4 was t. x5 is s. And x6 is 1/3. So that is our solution in column form, but we're going to actually add one more comment just to make it clear to the reader, because somebody might read this and think, whoa, 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 what is U, what is T, and what is S? We've never talked about those letters. So you want to be clear that those are not some new variable that have been introduced. They are just placeholders for arbitrary values. Here, they could be anything, right? That's our way of saying that x2, oops, I got the wrong button here. That's our way of saying that x2, x4, and x5 could be anything. And once you assign values to those variables, well, then they will determine the values that x1, x3, and x6 must take on. Well, in this case, x6 is already going to be 1/3, but that will dictate what x1 and x3 have to be in order to make sure the system is satisfied. So what you usually do is you just say where s, t, and u, which are real numbers. I'm just going to say that s, t, and u belong to the real numbers. I can just say I can say they're parameters, or I can say they're arbitrary. That kind of accomplishes the same thing. I like to use the word arbitrary, which just means They can be anything the reader wants them to be. So whoever's reading this, presumably they wanted to get solutions to this linear system. So this is telling them how to generate all the solutions to the linear system we started with, the one that had 4 variables and 6 equations. I mentioned right off the bat, I said this system here is going to be one of the systems where we actually have infinitely many solutions, and I told you that this example would serve as a way to demonstrate how to keep all those solutions organized. This is how you do it. This is figuring out which variables are free. That means the variables that can be anything, right? X2, X4, and X5 could be absolutely anything. But then the basic variables are the ones that have to now be determined based on the values of the free variables. Or in the case of X6, it just has to be 1/3. So that one it's pinned down as that value. But so that in a sense it's the opposite of being free. But by saying that to the reader, saying, okay, U, T, and S, you could pick those to be whatever you like, but then once you do that, here's a formula for determining what X1 is, here's a formula for determining what X3 is, and here's a formula for determining what X6 is. And once you do that, you're going to get yourself a solution. And the idea is this now describes all the solutions to that linear system.